The falling cat problem is a problem that consists of explaining the underlying physics behind the observation of the cat righting reflex. That is, how a free-falling body can change its orientation such that it is able to right itself as it falls to land on its feet, irrespective of its initial orientation, and without violating the law of conservation of angular momentum. Although amusing and trivial to pose, the solution of the problem is not as straightforward as its statement would suggest. The apparent contradiction with the law of conservation of angular momentum is resolved because the cat is not a rigid body, but instead is permitted to change its shape during the fall owing to the cat's flexible backbone and non-functional collarbone. The behavior of the cat is thus typical of the mechanics of deformable bodies. The rotation angle of the front body is larger than that of the rear body. The dynamics of the falling cat have been explained using the Udwadia-Kalaba equation. The falling cat problem has elicited interest from famous scientists including George Gabriel Stokes, James Clerk Maxwell, and Étienne-Jules Marey. In a letter to his wife, Catherine Mary Clerk Maxwell, Maxwell wrote, "There is a tradition in Trinity that when I was here I discovered a method of throwing a cat so as not to light on its feet, and that I used to throw cats out of windows. I had to explain that the proper object of research was to find how quick the cat would turn round, and that the proper method was to let the cat drop on a table or bed from about 2 inches, and that even then the cat lights on her feet." Whereas the cat falling problem was regarded as a mere curiosity by Maxwell, Stokes, and others, a more rigorous study of the problem was conducted by Étienne-Jules Marey, who applied chronophotography to capture the cat's descent on film using a chronophotographic gun. The gun, capable of capturing 12 frames per second, produced images from which Marey deduced that, as the cat had no rotational motion at the start of its descent, the cat was not cheating by using the cat handler's hand as a fulcrum. This in itself posed a problem as it implied that it was possible for a body in free fall to acquire angular momentum. Marey also showed that air resistance played no role in facilitating the righting of the cat's body. His investigations were subsequently published in Comptes Rendus, and a summary of his findings were published in the journal Nature. Marey thinks that it is the inertia of its own mass that the cat uses to right itself. The torsion couple which produces the action of the muscles of the vertebra acts at first on the forelegs, which have a very small motion of inertia on account of the front feet being foreshortened and pressed against the neck. The hind legs, being stretched out and almost perpendicular to the axis of the body, possesses a moment of inertia which opposes motion in the opposite direction to that which the torsion couple tends to produce. In the second phase of the action, the attitude of the feet is reversed, and it is the inertia of the forepart that furnishes a fulcrum for the rotation of the rear. Despite the publication of the images, many physicists at the time maintained that the cat was still cheating by using the handler's hand from its starting position to right itself, as the cat's motion would otherwise seem to imply a rigid body acquiring angular momentum. The solution of the problem, originally due to Kane and Schur, models the cat as a pair of cylinders capable of changing their relative orientations. Montgomery later described the Kane-Schur model in terms of a connection in the configuration space that encapsulates the relative motions of the two parts of the cat permitted by the physics. Framed in this way, the dynamics of the falling cat problem is a prototypical example of a non-holonomic system, the study of which is among the central preoccupations of control theory. A solution of the falling cat problem is a curve in the configuration space that is horizontal with respect to the connection with prescribed initial and final configurations. Finding an optimal solution is an example of optimal motion planning. NASA sent cats up on its Vomit Comet in the 1960s to better understand how the best internet meme can handle trying to land in zero gravity. It's universally understood that cats can consistently land on their feet, mainly because can use their own body as a flexion. Meaning cats will pivot the front half of their body, from the waist to the face, independently from the back portion of their body. Then the back portion of the body will follow soon after, with their tail circling at the end as correcting force. Scientists were curious how cats would behave free fall knowing their Earth-like free-falling behavior. Because as it turns out, a cat's renowned ability to always land on its feet is worth exactly zip when its airplane is plummeting towards the planet's surface at 9.8 meters per second squared. Watching them try to figure that out, especially when the experiment has been captured on old-school 8mm film, makes for some truly entertaining